But how the crystal look like? For that, I will have to take the help of microscopy. 120 hours, the crystal appeared subscribing. This is this crystal. Do you see? That is the 100 axis, and the other one is the 010 axis. And this is the diffraction pattern. You put the diffraction pattern and the crystal parallel like this. The crystal, when you see on the microscope screen, like this is the screen, and the crystal is looking like this, right? It is the crystal. When I'm in the image mode, I take the image of this crystal, and it was this, right? Then I change it to the diffraction mode, and without changing the orientation, and I got the diffraction pattern like this. This direction give me the b-axis, and that direction give me. So I put the crystals parallel, the crystal image and the diffraction parallel in the same orientation, and then I say that this is the a-axis, this is the b-axis, this is the c-axis. When you change the mode, or when you change the magnification in the machine, the orientation of the crystal changes. So be careful about that. Secondly, when you are presenting your data, I frequently observe that you had crystals like this in the original image. And when you work in a field for 20 years or 30 years, you know many things. So if a person brings to me crystals of that shape, and they are like this, or like this, then suddenly it strikes my mind that this should not be that. So what happens? The crystals are usually like this, but what the student do, they increase the image in one dimension more and leave the other the same, and these nearly cuboidal type crystals appear like this when you expand one dimension and leave the other the same. So you are really damaging the data. Never change the image in an odd manner. If you are changing it, then the dimension, every dimension should be equally increased or enlarged. Then the true information will come. What I was telling you, I saw this small crystal occasionally, that after 120 degree, 20 hours at this temperature. Then I went to 217 hours. So I increased the number of the same phase. Then I looked in the transmission electron microscope that how these crystals appear here, right? These are the various phases. And here I heated this material for, I don't remember exactly, but it was about 476 degrees Celsius for 2 hours. Right? 476 and 454. 20 degree, 22 degree change crystallized most of this material in 2 hours, which couldn't be crystallized to that level after 408 hours at 454. So this is how people play with the materials and how people tailor the microstructure, how people tailor the composition, how people tailor the properties of materials. And this is the difference. 1% phosphorus pentoxide and no phosphorus pentoxide, and it was a high temperature for longer time, it was at a lower temperature for shorter time. But look at the difference in crystal size and look in the difference in the number of crystals. I increased the number of crystals by adding phosphorus pentoxide as the nucleation agent. but increase the viscosity of the sample because phosphorus increases the viscosity. When the viscosity increases, the mass flow is restricted. When the mass flow is restricted, the formation of large crystals is restricted. When the formation of large crystal is restricted, you make more crystals at the same time. Because local reorientation is possible, but long range ordering is not possible. So you play with the size. And why a material forms spherical crystals and why the other forms elongated crystals? When you are in a highly viscous medium, you move equally in every direction, and the movement is very slow, so it favors a spherical symmetry. But when you are in a fluid medium, then in any direction, the longer axis will take you, but not the longer. If, for example, this unit cell, this was ABC. This C is 15 angstrom, this is 5 angstrom, latest parameter of a unit cell, and this is say 4 angstrom. Then common sense says that this crystal will grow more in this direction because the addition of a single plane increases the dimension by 15 angstrom in comparison to other. But no, this is not true in many cases. And the direction along which a plane can be added requiring less energy will preferably form. The plane which requires less energy will preferably form. So if it requires, for example, 1 MeV energy, right? Or say some other amount, and adding a plane along this direction needs a couple of times more, then this will preferentially form, this will grow along this direction preferentially in comparison to this. So this will be the elongated direction and this will be the breadth of the crystal, right? So this image was published in 1998 or 97 on the top of the Material Science Journal. And that was a very poor image I had taken, but it had that much value in those days because I had shown practically that what the phosphorus pentoxide did with the sample. How did it increase the nucleation rate and how did it constrain the size of the crystal. This material is much mechanically stronger than this, right? Now, when you go further, look back, look here, look here. This is optical microscope, right? This is 20 micrometer, so the crystal size is about 20 micrometer. Here, this is 20 micrometer, this scale. How do you say this is 20 micrometer and this is 10 micrometer? This is a crystal. The scale is this, 20 micrometer scale. So you have a scale bar on the image. And this is a crystal. So now I take how much is this? This is, for example, 1 centimeter and this is 3 centimeter. So the breadth of this crystal is 60 micrometer. Then look into this direction. It is, for example, 1.5 of this scale bar. 1.5 of this scale bar is 30 micrometers. So if you see the crystal dimensions, the crystals were about 1 micrometer. This is wrong. Crystal is not a thin needle. If you are talking of the length, then it's okay. But my opinion is, as a microscopist, always write the shorter dimensions of the crystals ranged between, for example, say 25 and 35 micrometers. Because when you measure the dimensions of several crystals and you are averaging it, then you say the shorter dimensions of the crystals range between 25 and 35, and this range between 55 and 65. This is the more scientific description of the size of a crystal. But if you say that the crystal was 100 micron long, then it is not enough, because the crystal is not usually a needle. If it is exactly a needle and the other dimensions are almost zero, then you can say. But if the dimension is zero, then how will you explain it? Can one dimension be zero? Right? So always never believe what other people write. Think yourself that if I am saying, I am repeating, I am writing this particular sentence about this feature I have seen, is it logically correct? If a scientist asked me and I put these two images in front of him and I have written something else and there is something else, how will I justify it? I am telling you the truth. One of my students wrote a paper and he brought it to me. I told him I am not convinced with that, what you say. He brought a lot of other people with him and told me that people have published worse paper than this. Why are you not allowing me to submit it? I told him I am not convinced. What you are saying is wrong, scientifically and logically. He submitted that paper and it was published. This never means that I was wrong, because the reviewer was wrong who accepted that paper. Right? So never ever write something which is not correct. Always give a proper logic. If all the other people are doing wrong, will you follow them? Never. Correct their path. It is in the best interest of the wrongdoer as well as yours. Right? In science, when you write something, bring before the scientific community that all the scientists and relevant experts are sitting there. Will I be able to justify my statement? If yes, then write it with full confidence. But if no, then never write it. Discuss it with people. What can be a better statement? For example, I measured this crystal and I said the crystal dimensions were 30 into 60 micrometers square. This was the easiest statement I could write. But if I have another crystal here, then it is 120 angstrom long, micrometer long. Then another is 20 micrometer broad. Then will this statement explain that? I will not be able to justify that. So why not put a range? There are always a way. There is always a way to describe this, your observation, your experimental result more precisely if you give time to it. And if you read others' works, that how people describe their observations, then check it, that are they correct? If yes, then follow them. If not, then find out your own way, which is more realistic and more correct. Then, after that, this was the outcome of the phosphorus pentoxide. If you remember, the same, it is this crystal, the phosphorus pentoxide one, and by 1 mole phosphorus pentoxide, I changed the morphology of this crystal from this to this. So what I did, I squeezed down the dimensions of the crystal. I changed the crystal morphology for more elastical to less elastical. I brought it close to the spherical symmetry. So what I did, I increased the viscosity and I increased the nucleation rate. So you can play with the nucleation rate and you can play with the viscosity of the material. So the material engineer is a good number of ways to reach the ultimate end. Now, twinning mechanism, how the crystal grows. It grows by a twinning mechanism. Twin planes are the one that when you put a mirror here and this half looks as the mirror image of this, then they are called twins. Put a mirror image here and this is a mirror image of this. It is twinning. If it is not, then it is not twinning mechanism. This, the one which occurs at 110 direction, which is the 100 direction of the daughter crystal. The 100 direction of the daughter crystal and the 110 direction of the parent crystal. So the twinning plane is the one which is associated with the parent crystal. So the 110 direction, the plane, is the twinning plane and the crystal originates from there. This is the daughter crystal, this is the parent crystal. And why I am saying this? Because I took the diffraction pattern at the junction. And that junction gives completely the same direction. If this is 100, confirmed by the diffraction pattern. And this is 100, confirmed by the diffraction pattern. So when you say something, you must have an evidence for it. Scientific evidence for it. The machine is completely calibrated. The machine is fully calibrated. You have a proper calibration scale. If you don't have a calibration, for example, you put a sample in XRD and the machine is 0.5 degree error. Do you mean what that means? It is showing you 4 angstrom, 4.5 angstrom. So everything is wrong. Because between 4 angstrom and 4.5 angstrom, there may be a lot of other parameters. And your result will not be explainable by the scientific logic. So always try to use calibrated equipment. I was looking to find, as you remember, I yesterday told you that phosphorus pentoxide made the crystallization easier by first forming the lithium phosphate Li3PO4 crystal nuclei, which provided epitaxial crystallization sites for the crystallization of the metric phase. So lithium phosphate crystal formed, and I give you the example that I am raising myself to this table. I want to sit here, but if I sit here, it will need a lot of force, a lot of energy. But if there is a couple of steps, with a little effort, I will sit on this table. Li3PO4 is doing the job of the step. It has some plane, crystallographic plane, where the lithium disilicate plane sits very well with ease. When that ease is provided to it, so everywhere lithium disilicate material comes and sits on that plane and preferentially and multiply increase the nucleation rate of the material. But lithium orthophosphate crystal is very difficult to see because I am saying it is the first nucleus. If the first nucleus is forming in a very viscous medium, the size will be very, very small. The size will be very, very small. So as a scientist, I am thinking, what? Somebody was saying something. Okay, so as a scientist, I should think how to increase the size of that crystal. And I told you that decrease the viscosity, increase the fluidity, the mass transfer will become easier. When the mass transfer becomes easier, the crystal will go faster. So what I did here, as I told you, that I put more less lithium silicate here and more phosphorus here. It decreased the size. But when I increase the lithium silicate content, I decrease the viscosity, I increase the fluidity, and I increase the size of the crystal. So this is science, this is engineering, that you can play and you can do many things, but all must be supported by an authentic, logical, justifiable theory. If there are many people